March 17, 1942, 2:30 a.m., Cambridge, Massachusetts, Building 22, MIT Radiation Laboratory. Luis Walter Alvarez hunched over an oscilloscope whose green phosphor glow was the brightest light in a room that smelled of solder flux, overheated vacuum tubes, and coffee that had been reheated on a hot plate so many times it had acquired the consistency of motor oil. His eyes burned from 16 hours of continuous work. His fingers were stained with the residue of electrical components he had assembled, disassembled, and reassembled in configurations that textbooks said should not function, but that experimental reality suggested might. Alvarez was 30 years old, the son of a physician at the Mayo Clinic who had raised his boy to believe that problems existed to be solved, and that solving them required the willingness to be wrong repeatedly until you were finally right. He had earned his doctorate in physics at the University of Chicago, had worked at Berkeley's radiation laboratory under Ernest Lawrence, had published papers on nuclear physics that established his reputation among the small community of American scientists who understood such things. 3 months earlier, he had been studying cosmic rays. Now he was trying to build a radar system that would allow aircraft to land when pilots could not see the ground. The problem was not theoretical. Alvarez understood the physics of radio waves, knew how electromagnetic radiation bounced off objects and returned to receivers that could calculate distance and direction from the time delay. The British had proven that radar worked. Their chain home stations had helped win the Battle of Britain by detecting German aircraft before they reached English shores. The problem was practical, a matter of translating principles that functioned in laboratory conditions into equipment that functioned in the chaos of actual warfare, operated by men who were not physicists, in aircraft that vibrated and rolled and filled with the noise of engines and the terror of combat. The specific challenge consuming Alvarez's attention that night was ground-controlled approach, a system that would allow radar operators on the ground to guide aircraft to safe landings when weather made visual approach impossible. Pilots died in fog, they died in rain, they died in the low clouds that rolled across English airfields where bombers returned from missions over Germany, their fuel exhausted, their crews wounded, their options reduced to landing blind or crashing. A system that could talk those aircraft down, that could tell pilots their exact altitude and heading and distance from the runway, would save more lives than any weapon the laboratory might produce. The irony that Alvarez could not have articulated in March 1942, but that historians would later recognize as defining, was that the United States had entered the war technologically behind in precisely this field. British radar was more advanced. German radar had capabilities that American systems could not match. The Cavity Magnetron, the device that made microwave radar possible, had been invented in Birmingham, not Boston. American scientists had been working on radio detection since the 1930s, but their efforts had been scattered across military services that did not share information, academic institutions that did not coordinate research, and industrial laboratories that guarded discoveries as proprietary secrets. What America possessed was less tangible than any specific technology, a system for producing technologies that did not yet exist. The building where Alvarez worked had not existed 18 months earlier. The laboratory that employed him had been created from nothing in November 1940, had grown to over 2,000 researchers by the night he sat before his oscilloscope, would eventually employ nearly 4,000 scientists and engineers working on radar systems whose applications multiplied faster than organizational charts could document. The radiation laboratory was not merely a facility, it was a demonstration that innovation could be organized, that creativity could be systematized, and that the chaos of discovery could be channeled toward objectives that military necessity defined. 6 miles to the east, in a Moscow that German armies had nearly reached before winter and counteroffensive pushed them back, Another scientist was attempting to solve similar problems with resources that made Alvarez's laboratory seem luxurious. Axel Berg had been a prisoner 3 years earlier, accused of crimes he had not committed, awaiting execution in cells where the smell was not solder and coffee, but concrete and fear. He had been released because the men who could have replaced him were dead, and the Soviet Union suddenly needed radio engineers more than it needed confessions. October 14, 1941, 4:15 p.m., Moscow, People's Commissariat of the Navy, Radio Engineering Laboratory. Axel Ivanovich Berg sat at a desk covered with technical diagrams that represented possibilities rather than realities, in a room that smelled of dust, electrical insulation, and the particular staleness of a facility whose windows had not been opened since the war began. The October light filtering through glass that had been taped against bomb blasts gave everything a yellowish cast, as if the documents he studied were already historical artifacts, rather than plans for technologies that might determine whether the Soviet Union survived the winter.
Berg was 48 years old, a former Tsarist naval officer from Orenburg, whose career had traced the convulsions of Russian history with a fidelity that left scars both visible and hidden. He had served on submarines during the First World War, had transferred his loyalty to the Bolsheviks when transfer became the only alternative to execution, had built a reputation as one of the Soviet Union's foremost radio engineers through 2 decades of work that combined theoretical sophistication with practical application. He had been arrested in December 1937, accused of participating in a military conspiracy that existed only in the imaginations of interrogators whose promotion depended on discovering conspiracies. He had been released in May 1940, rehabilitated without explanation, restored to positions that his imprisonment should have permanently foreclosed. The release had not been mercy. The purges that had consumed the Soviet military and scientific establishments had killed or imprisoned so many radio engineers that the survivors had become irreplaceable. Berg's expertise, which had made him valuable enough to arrest when arrests demonstrated vigilance, now made him valuable enough to release when the alternative was having no one capable of building the equipment that modern warfare required. The technical diagrams on his desk documented what Soviet radar could not do. German aircraft had been bombing Moscow for 3 months, approaching through darkness that Soviet air defenses could not penetrate, dropping explosives on a capital whose early warning systems relied on observers with binoculars and telephone lines that German raids had repeatedly severed. The British had radar that detected aircraft at distances exceeding 100 kilometers. The Germans had radar that guided night fighters to bombers they could not see. The Soviets had theoretical knowledge of how such systems functioned and almost no capacity to manufacture them. Berg understood the physics as well as any scientist in Britain or America. Soviet researchers had been experimenting with radio detection since the early 1930s, had published papers, had conducted demonstrations that proved the principles worked. The problem was not comprehension, the problem was production, the transformation of laboratory prototypes into equipment that could be manufactured in quantities that mattered, operated by soldiers whose training could not assume university education, maintained in conditions that included mud and snow and the constant vibration of military vehicles. The institutional obstacles were worse than the technical ones. Berg could requisition vacuum tubes only by submitting requests that passed through multiple approval authorities, each one staffed by officials whose survival depended on questioning whether requests might conceal sabotage or waste. A resistor that Alvarez could obtain in Cambridge with a signature required Berg to justify in written memoranda that explained why the component was necessary, why alternatives would not suffice, why the quantity requested was not excessive. The paperwork consumed time that development required. The suspicion consumed trust that collaboration demanded. His research staff included brilliant scientists whose theoretical capabilities matched anyone working at MIT. They worked in fear that Berg recognized from his own imprisonment, the particular caution of men who understood that failure might be interpreted as intentional, that mistakes might be characterized as deliberate, that the boundary between technical setback and prosecutable treason was determined by officials who understood nothing of the work they judged. Initiative was dangerous. Experimentation was suspect. The freedom to fail that innovation required was precisely what the Soviet system could not provide. Berg had been ordered to develop radar that matched German and British capabilities. He had been given resources that could not accomplish this objective and constraints that guaranteed his efforts would fall short. The men who had arrested him were still in positions of authority. The system that had nearly killed him was still functioning. He would do what he could with what he had, and he would document everything in reports that might protect him when the inevitable questions arose about why Soviet radar remained inferior to what the capitalist nations had produced. June 12, 1940, 4:30 p.m., Washington, D.C., the Oval Office. Vannevar Bush waited in a chair outside the president's office, holding a single sheet of paper that represented either the future of American science or the end of his credibility with the most powerful man in the country. The corridor smelled of floor polish and the particular institutional cleanliness of buildings where history accumulated in documents rather than artifacts. His hands were steady, but the steadiness required conscious effort. He had spent months arguing that the United States needed to reorganize how it developed military technology. He had 15 minutes to convince Franklin Roosevelt that a former engineering dean from Massachusetts understood warfare better than the generals who had spent their careers studying it. Bush was 50 years old, the son of a Universalist minister from Everett, Massachusetts, who raised his children to believe that problems yielded to systematic analysis and that systematic analysis was a moral obligation. He had earned degrees from Tufts and MIT, had built a mechanical computer called the differential analyzer that could solve equations no human could calculate by hand, had risen to become dean of MIT's School of Engineering and then president of the Carnegie Institution of Washington. He understood how research institutions functioned, how scientists thought, how discoveries moved from laboratory curiosities to practical applications. He also understood that the American military had no idea how to manage the process. The problem Bush had identified was organizational rather than intellectual. American scientists were as capable as their counterparts anywhere in the world. American universities contained expertise in physics, chemistry, engineering, and mathematics that matched or exceeded what any European nation possessed. American industry could manufacture anything that could be designed in quantities that dwarfed what smaller economies could produce. The pieces existed. The system for assembling them did not. Military research in 1940 was controlled by military officers who distrusted civilian scientists, who believed that weapons development belonged to arsenals and proving grounds rather than universities, who filtered research priorities through bureaucratic processes designed for procurement rather than innovation. A scientist with an idea had to convince officers who did not understand the science that the idea was worth pursuing, then wait while committees evaluated proposals according to criteria that had nothing to do with technical merit. The Army and Navy maintained separate research establishments that did not share information. Academic institutions competed rather than collaborated. Industrial laboratories guarded discoveries as trade secrets. The result was duplication, delay, and the systematic suppression of exactly the unconventional thinking that breakthrough technologies required. Bush's proposal, typed on the single sheet he carried, was radical in its simplicity. Create a civilian organization that reported directly to the president, bypassing the military chain of command entirely.
Staff it with scientists who would choose their own research priorities, who would decide which problems were worth solving and which approaches were worth attempting. Fund it with money that did not require congressional appropriation for each project. Allow it to fail repeatedly because failure was how science actually worked, because the path to success ran through experiments that did not produce the expected results. The meeting lasted approximately 15 minutes. Roosevelt read the proposal, asked questions that demonstrated he understood its implications, and approved it with a handwritten notation that Bush would preserve for the rest of his life. The National Defense Research Committee came into existence that afternoon, created by presidential authority that circumvented every obstacle the military bureaucracy might have raised. Bush became its chairman, empowered to recruit scientists, allocate resources, and direct research toward objectives he considered essential. The decision would prove to be among the most consequential Roosevelt ever made. The NDRC and its successor organization, the Office of Scientific Research and Development, would oversee the development of radar systems that Alvarez and thousands of others would create, of proximity fuses that would revolutionize artillery warfare, of penicillin production methods that would save countless wounded soldiers, and ultimately of the atomic bomb that would end the war in the Pacific. The organizational innovation that Bush proposed would produce more technological innovation than any structure any nation had ever created. Axel Berg, working in Moscow under constraints that Bush could not have imagined, would spend the war demonstrating what happened when the opposite organizational philosophy prevailed. The MIT radiation laboratory that Luis Alvarez worked in through 1942 and 1943 grew faster than any research institution in history, expanding with a velocity that organizational theorists would later study as a case of managed chaos producing extraordinary results. The building he had entered in early 1942 as one of several hundred researchers became a complex that eventually sprawled across 15 acres of Cambridge real estate, housing laboratories that multiplied like cells dividing, each one spawning subspecialties that spawned their own subspecialties, until the organizational chart resembled a living organism rather than a bureaucratic hierarchy. Alvarez experienced the growth as a constant negotiation between ambition and resources, between what the physics said was possible and what the engineering could actually deliver. His ground-controlled approach project consumed months of experimentation that produced failures he documented with the same precision he applied to successes. Oscilloscopes burned out, transmitters overheated. Antenna designs that performed perfectly in laboratory conditions produced unusable signals when mounted on actual aircraft. Each failure taught something. Each lesson required another failure to verify. The process was expensive, time-consuming, and absolutely essential. The system that Vannevar Bush had created allowed this process to continue without the interruptions that military oversight would have imposed. When Alvarez needed components, he requisited them through a procurement system designed to eliminate delays rather than prevent waste. When he needed personnel, he recruited from universities, whose faculty understood that the war effort took precedence over academic schedules. When he needed to test equipment in conditions the laboratory could not simulate, he arranged field trials with military units, whose commanders had been instructed to cooperate with civilian scientists whose authority derived from Bush's organization rather than military rank. The smell of the laboratory changed as Alvarez's project progressed. The original odors of electrical work gradually supplemented by the machine oil and aviation fuel that clung to equipment returned from field tests. Technicians who had never seen an aircraft learned to install radar systems in bombers whose crews would depend on those systems to survive. Engineers who had designed circuits on paper learned to redesign them when pilots reported that controls were inaccessible or displays were unreadable in the conditions that combat actually produced. The feedback loop between laboratory and battlefield accelerated development in ways that peacetime research could never have achieved. 6,000 miles away, Axel Berg was learning what the absence of such feedback meant for Soviet radar development. His laboratory received reports from the front that described German capabilities without providing captured equipment to analyze. His researchers developed prototypes that could not be tested because the military units that might have tested them could not spare aircraft or personnel for experiments whose value had not been proven. The circular logic was paralyzing. Equipment could not be tested until it was proven effective, but effectiveness could not be proven without testing. The institutional constraints were worse than the logistical ones. Berg submitted proposals through channels that required approval from officials whose technical understanding was limited and whose political caution was unlimited. A request for vacuum tubes triggered questions why existing tubes were insufficient. A request for additional researchers triggered questions why existing staff could not accomplish the work. Every requisition was an opportunity for someone to demonstrate vigilance by questioning whether the request concealed waste, incompetence, or deliberate sabotage. Berg watched younger scientists learn the survival skills that innovation could not accommodate. They proposed projects that were certain to succeed rather than projects that might produce breakthroughs. They documented everything in language designed to deflect blame rather than communicate clearly. They avoided collaboration with researchers in other institutions because collaboration meant sharing information, and shared information could be used by rivals to claim credit or assign fault. The system that had imprisoned Berg and killed so many of his colleagues continued shaping behavior long after the immediate terror had subsided. The production numbers that accumulated through 1942 and 1943 documented the consequences. American factories manufactured radar equipment in quantities measured in tens of thousands of units. Soviet factories produced hundreds. The gap was not capability. Soviet workers were as skilled as American workers. Soviet engineers understood the same physics. The gap was organizational, a matter of systems rather than individuals, of trust rather than talent. September 29, 1940, 11 a.m., Washington, D.C., Shoreham Hotel. The black metal box that changed the war sat on a conference table in a room that smelled of cigarette smoke, furniture polish, and the particular tension of men who understood they were participating in something unprecedented. The box measured approximately 14 inches across and weighed less than 15 pounds. It contained a device called a Cavity Magnetron, and the British scientists who had carried it across an Atlantic Ocean prowled by German submarines were about to give it to a nation that was not yet their ally. Sir Henry Tizard led the delegation, a 65-year-old chemist who had spent months convincing Churchill's government that Britain's survival depended on sharing its most closely guarded secrets with Americans who might use them to produce weapons Britain could no longer manufacture itself. The mission he commanded carried documentation on jet engines, proximity fuse concepts, submarine detection methods, and the Cavity Magnetron that would prove more valuable than everything else combined. British scientists had invented the magnetron in February 1940, had recognized immediately that it made microwave radar possible, had understood that microwave radar would transform both air defense and offensive bombing. They neither had the industrial capacity nor the safety from German bombing to develop it themselves. The decision to share was not generosity, it was calculation, the recognition that secrets hoarded were secrets wasted if the nation hoarding them lost the war. Tizard's box contained the most advanced radar technology in the world, handed to American scientists and engineers who had been working on similar problems with inferior equipment, who suddenly found themselves holding the key to capabilities they theorized but could not achieve. The Cavity Magnetron produced microwave radiation at power levels that existing American technology could not approach. Within weeks of the Tizard mission's arrival, the MIT Radiation Laboratory had been founded specifically to exploit what the British had shared. Walter Alvarez would later describe the magnetron's arrival as the moment American radar development transformed from catching up to leaping ahead. The device that British scientists had invented became the foundation for systems that American industry manufactured in quantities that British factories could never have matched. The ground-controlled approach radar that consumed Alvarez's nights in 1942 existed because British scientists had chosen to trust Americans with knowledge that German intelligence would have paid any price to obtain. Trust multiplied capability. Secrecy would have preserved British priority while guaranteeing Allied defeat. The contrast with Soviet practice could not have been more complete. Stalin's government was nominally allied with Britain by June 1941, theoretically united against the common German enemy, supposedly cooperating in the shared project of Nazi destruction. The reality that Axel Berg experienced daily was an information environment where sharing knowledge between Soviet institutions was nearly as difficult as obtaining it from foreign adversaries. Berg's laboratory in Moscow could not freely access research conducted by the Army's radar development teams. Army researchers could not access Navy research without approvals that required weeks to obtain, and justifications that invited scrutiny of why the information was needed. Each institution guarded its discoveries not because secrecy served military purposes, but because information was currency in a system where survival depended on demonstrating value that rivals could not claim. A researcher who shared a breakthrough with another institute risked having that institute claim credit. A laboratory director who collaborated too freely risked questions about why his own staff could not accomplish the work independently. The paranoia extended to foreign intelligence that might have accelerated Soviet development. Reports describing British and American radar capabilities reached Moscow through espionage networks whose information could not be openly distributed because acknowledging how it had been obtained would compromise sources whose continued operation was deemed more valuable than any single technical advantage. Berg received summaries of captured German equipment that other laboratories had analyzed, but he could not examine the equipment itself because the laboratories that possessed it would not release materials that demonstrated their own importance. The Americans, meanwhile, were building an innovation pipeline where information flowed freely because Vannevar Bush had designed it to flow freely. Researchers at MIT shared results with colleagues at Bell Labs, at Westinghouse, at university facilities across the country. The assumption underlying the entire system was that shared knowledge produced faster progress than hoarded knowledge, that collaboration accelerated development, that trust was more efficient than suspicion. The assumption proved correct. The proximity fuse that emerged from Vannevar Bush's organizational system represented perhaps the most remarkable technological achievement of the war, a device so secret that American commanders were forbidden to use it in situations where unexploded rounds might be recovered by enemy forces. The concept was simple to describe and extraordinarily difficult to execute. An artillery shell that detected when it was close to a target and detonated automatically, without requiring direct impact. The implications were revolutionary. Anti-aircraft guns that had required direct hits against fast-moving aircraft could suddenly destroy targets they merely approached. Artillery barrages that had relied on statistical probability to hit dispersed infantry could suddenly detonate at optimal heights above the ground, maximizing fragmentation effects. Bush had authorized proximity fuse development in August 1940, before the radiation laboratory existed, before Pearl Harbor transformed American priorities, before the organizational systems that would produce Alvarez's radar had fully coalesced. The project migrated to Johns Hopkins University's Applied Physics Laboratory, where researchers confronted a problem that combined miniaturization, ruggedness, and precision in ways no previous engineering challenge had demanded. The fuse had to contain a radio transmitter, a receiver, an amplifier, and a triggering mechanism in a package small enough to fit in an artillery shell. It had to survive being fired from a gun, experiencing accelerations that exceeded 20,000 times the force of gravity. It had to function after storage in conditions ranging from tropical heat to Arctic cold. It had to be cheap enough to manufacture in millions. The engineering obstacles were immense. Vacuum tubes, the only amplification technology available in 1940, were fragile glass containers that shattered when subjected to shock. The researchers developed ruggedized tubes, whose components were supported by structures that absorbed impact rather than transmitting it. Batteries that powered the fuse had to remain inert during storage, then activate instantly when the shell was fired. The solution involved electrolytes separated from electrodes by barriers that the firing shock would rupture, creating power precisely when power was needed. Each problem solved revealed additional problems whose solutions required further innovation. The first proximity fuses reached combat in January 1943, 18 months after serious development began. The speed was unprecedented. The production numbers that followed were staggering. American factories manufactured over 22 million proximity fuses before the war ended, devices that transformed anti-aircraft defense and artillery bombardment into sciences of predictable lethality rather than statistical probability. The fuses that destroyed Japanese kamikaze attacks in 1944 and 1945 saved ships and sailors in quantities that no one could precisely calculate because the calculation required knowing how many would have died without the technology. Axel Berg learned of the proximity fuse through intelligence reports that reached his Moscow laboratory in fragments whose significance he immediately grasped. The concept was not beyond Soviet theoretical understanding. Soviet scientists comprehended radio transmission, understood proximity detection, could diagram how such a device should function. The problem was not knowledge, the problem was everything else. Manufacturing a proximity fuse required industrial capabilities that Soviet factories had never developed. The ruggedized vacuum tubes demanded precision machining that Soviet equipment could not achieve. The miniaturized components required manufacturing tolerances that quality control could not maintain. The batteries needed chemical compounds whose production Soviet industry had never prioritized. Each element of the American achievement rested on industrial infrastructure that decades of development had created, infrastructure that could not be improvised regardless of how urgently the need was recognized. Berg submitted reports documenting what Soviet industry would need to replicate the American fuse. The reports passed through channels where officials questioned why Soviet scientists could not develop indigenous solutions, where requests for foreign equipment triggered suspicions about defeatism or excessive admiration for capitalist technology. The institutional obstacles that had slowed radar development made proximity fuse development effectively impossible. The Soviets manufactured 0 proximity fuses during the war. They would not achieve production capability until years after the conflict ended. The disparity illuminated everything that distinguished the two systems. American production succeeded because Bush had created organizations where failure was tolerated, where information flowed freely, where resources followed promising ideas rather than political priorities. Soviet production failed because the system that governed Berg's laboratory could not tolerate failure, could not permit free information flow, could not allocate resources without approvals that innovation could not survive. The proximity fuse was not merely a weapon, it was a demonstration that organizational design determined technological capability. The consequences of organizational difference became visible in the skies over Europe and the battlefields of the Eastern Front through 1944 and into 1945, measured not in abstract comparisons, but in aircraft that landed safely or crashed, in artillery that coordinated effectively or killed friendly troops, in communications that connected commanders or dissolved into static at moments when connection meant survival. Luis Alvarez watched his ground-controlled access radar system save lives with a regularity that transformed experimental technology into operational necessity. Each successful landing represented a crew that would have died before his invention existed. The GCA system that Alvarez had developed through those sleepless nights in Cambridge reached operational deployment in the fall of 1943. Controllers sitting in trailers at English airfields watched blips on screens that represented bombers returning from Germany, aircraft whose pilots could not see runways obscured by fog that rolled across the English countryside with the reliability of tides. The controllers spoke into microphones, their voices carrying across radio frequencies to cockpits where exhausted men followed instructions that contradicted every instinct their eyes provided. Turn left 2 degrees. Descend to 400 feet. You are 1 mile from the runway. The voices guided aircraft through soup so thick that pilots did not see the ground until their wheels touched it. The smell in those control trailers was coffee, cigarette smoke, and the particular tension of men who understood that their words determined whether other men lived or died. Each instruction had to be precise. Each response had to be immediate. A controller who hesitated, who second-guessed his instruments, who trusted his assumptions over his equipment, could talk an aircraft into the ground instead of onto the runway. The technology that Alvarez had built was only as good as the men who operated it, and the training programs that prepared those men were only as good as the organizational systems that developed the training. Alvarez received reports documenting what his system accomplished. Hundreds of aircraft landed safely in conditions that would have previously meant circling until fuel exhausted, or attempting approaches that killed crews whose luck finally failed. The numbers accumulated through months of operations, each successful landing a data point that validated the investment Bush's organization had made. Each crew that walked away from their aircraft a testament to what coordinated research could achieve. The technology had moved from oscilloscope to operational deployment in less than 2 years, a pace that peacetime development could never have matched. The Eastern Front told a different story. Soviet communications remained primitive by comparison, not because Soviet engineers lacked understanding, but because the systems that should have produced advanced equipment could not function as American systems functioned. Radio sets that worked in laboratory conditions failed in the mud and cold of actual combat. Frequencies that should have been secure were compromised because coordination between units could not be maintained. Commanders lost contact with subordinates at moments when contact was essential, issued orders to formations that had already moved or been destroyed, fought battles whose fog was thickened by technology that could not penetrate it. The friendly fire incidents documented in Soviet records revealed what communications failure meant in human terms. Artillery barrages fell on positions that friendly troops had captured hours earlier, killing soldiers whose advance had not been reported through systems that had broken down. Aircraft attacked columns that wore the wrong insignia because identification procedures could not be maintained across units whose radios operated on incompatible frequencies. The Americans found the casualty rates appalling when Lend-Lease brought them into contact with Soviet military operations. Lend-Lease itself illustrated the gap between equipment and capability. American radios, American radar sets, American communications equipment flowed to the Soviet Union in quantities that should have transformed military effectiveness. The Soviets could operate what Americans provided. They could not manufacture it. They could not repair it when it failed. They could not train technicians in numbers sufficient to maintain equipment whose complexity exceeded what Soviet technical education had prepared them to understand. The institutional capacity that Vannevar Bush had built could not be shipped across oceans. Only its products could be shared, and products without the systems that created them were temporary advantages rather than permanent capabilities.
Berg watched American equipment arrive and understood what its arrival meant about Soviet limitations. The war ended, but the systems that had fought it continued shaping the lives of the men who had built them. Luis Alvarez returned to Berkeley in 1945, to the radiation laboratory where Ernest Lawrence had pioneered particle physics before radar consumed the attention of physicists who might otherwise have spent the war years exploring the structure of matter. The laboratory smelled different now, less of electrical solder and military urgency, more of the particular patience that peacetime research permitted. Alvarez had spent 4 years building devices designed to kill efficiently or save lives immediately. He would spend the next 4 decades building devices designed to understand the universe. His post-war career traced a path that the wartime experience had made possible. The skills he had developed building radar systems transferred to particle accelerators, to bubble chambers that detected subatomic particles, to experiments that revealed structures no human eye could see. He won the Nobel Prize in Physics in 1968, recognized for contributions to elementary particle physics that built on techniques he had learned while trying to land bombers in English fog. The organizational systems that Vannevar Bush had created continued funding his research, continued trusting scientists to choose problems worth solving, continued tolerating failures that preceded breakthroughs. Alvarez died on September 1, 1988, in Berkeley, 77 years old, his life a testament to what happened when talent encountered institutions designed to amplify rather than constrain it. Axel Berg's fate illustrated what the Soviet system did to men whose abilities exceeded what the system could accommodate. He survived the war as one of the most respected electronics engineers in the Soviet Union, received promotions that recognized his technical contributions, accumulated honors that acknowledged what he had accomplished despite constraints that would have defeated lesser men. He became an admiral, a professor, a member of the Academy of Sciences whose opinion shaped Soviet electronics policy for decades. The laboratory smell of his final years was chalk dust and aging paper, the environment of an academic who had outlived the emergencies that had once made his expertise desperately valuable. But the system never fully trusted him, never permitted the freedom that innovation required, never stopped filtering his work through approvals designed to prevent the independent thinking that breakthroughs demanded. He published papers that Soviet censors reviewed before foreign colleagues could read them. He trained students who learned the same survival skills he had learned: the careful documentation, the conservative proposals, the avoidance of collaboration that might invite suspicion. The institutional constraints that had hampered his radar development continued constraining Soviet electronics long after the specific obstacles he had faced had been resolved. Berg died on July 9, 1979, in Moscow, 85 years old. His obituaries praised his contributions to Soviet science without acknowledging what those contributions might have been if the system had permitted him to work as Alvarez had worked, with resources that followed promising ideas and failures that taught rather than condemned. He had been brilliant. He had survived. He had accomplished less than his abilities warranted because accomplishment required conditions his country could not provide. Two systems had fought the same war with the same physics, the same theoretical knowledge, the same human capacity for invention and persistence. One had produced radar that guided aircraft home and proximity fuses that revolutionized warfare. The other had produced scientists who survived by limiting their ambitions to what approval processes would permit. The difference was not intelligence. The difference was trust, the willingness to let talented people fail repeatedly until they finally succeeded. The system that tolerated failure produced more success than the system that demanded it. This was not ideology. This was organizational physics, as measurable as any principle Alvarez had demonstrated in his laboratory.